Okay, I'm doing part D. So it says derive the vapor and the liquid phase of a Gibbs free energy of a compound that must be equal to its equilibrium. Okay. Okay, so our Gibbs free energy. So let's write a container. Show a container of our Gibbs. Show a container, a closed container. No heat is being added to this container. We also know that there's liquid in this container, and then there's vapor. So we know that there's moles of liquid, and then we know that there's Gibbs free energy of liquid, and then Gibbs free energy of vapor. Okay. And then there's moles of both. So we know that the moles equals the moles of the liquid and of the vapor. Also, if we take the derivative of this means that the differential change of the moles. So if we did differential change, what is this going to be? The differential change amount of moles in this container. No moles are being lost in this container since it's a closed container. So that means the change in moles is going to equal 0. So this will help us. So now let's write our equation. So we have our number of moles in the vapor phase times our Gibbs free energy in the vapor plus our moles in the liquid times our Gibbs in the liquid equals the amount of moles we have times our Gibbs. Okay, so now if we take the derivative of this, we get now we get the differential change of moles in the vapor equals our Gibbs in the vapor plus, and this is going to be product rules, so we're going to have our moles in the vapor times our differential change of the Gibbs in the vapor, and then we have our differential change of moles in the vapor times our Gibbs and the liquid, the liquid. And then we're going to have another product rule, so it's going to be the moles in the liquid times our differential change of Gibbs in the liquid. And then D. So the differential change on this amount of moles we just said is going to equal 0. So that's 0. So now the next thing that we want to do is we're going to combine like terms. So we know that the differential change in moles in the liquid is going to equal our Gibbs minus our Gibbs in the vapor. And this is going to be we're going to have a number of moles in the liquid, a number of moles in the vapor, and this is going to equal 0. So the next thing that we want to know is that this container is having no heat added to this. So no energy is being added to the system. So that means the differential amount of change of energy in the Gibbs of the vapor and in the liquid are going to stay the same since there's no heat added, so there's no energy being added to the system. So that means this is going to be the same. So this is also going to be 0. So now we just have DH equals GV minus GL equals 0. And then we can just solve for it, so it's GL equals GV. So now what this means is that our moles of Gibbs free energy in the liquid and our moles of Gibbs free energy in the vapor are going to equal each other. That means they are the same amount of energy in both. Also, it's saying that if you have a closed container of liquid and there's no heat being added to the system, that means our water vapor or liquid is going to be more, our water is going to be inclined to go for our liquid and our vapor. It's going to be favored to go for both. It doesn't matter what it wants. It's both equally favored to go for either. So that is this. And so the next thing that we want to do is we want to define our Clausius-Clapeyron equation. So the first thing that we know is that our Gibbs free energy in the liquid equals our Gibbs free energy in the vapor. We also know, let's derive our three equations that we have. So what we previously derived, we knew that T equals ds equals dq of reversible, right? We also know that du equals dq reversible minus p dv. So we can substitute it in. So now we know that du equals tds minus pvd. Okay, so after we know this, we also know that our enthalpy, so our enthalpy equals our internal energy plus our PV. So now let's take the let's differentiate it. So take the derivative of it. So then we have our differential amount of change of enthalpy. Then we have our differential amount of internal energy plus P. Well, let's do it. Yeah, P dV, and then we have our product rule. So then V dP. So now that we know this, we can plug this in for this. Now that we know our du, we can plug it in for du. So dH equals TdS minus P minus PdV plus PdV plus VPD. Cancel, cancel. So now you get dH equals TdS minus plus V dP. Okay. So now we know that. And our last thing that we know is okay, so the last thing that we know is we know our Gibbs energy equals our TdS The last thing we know is that our Gibbs free energy equals our enthalpy minus. The last thing we know is that our Gibbs free energy equals our enthalpy minus our TdS. So now if we take the derivative, we get dG equals dH minus TdS minus S dt. So now let's plug in our dH in this. So then we get the differential amount of change in our Gibbs energy equals TdS plus V dP minus TdS minus S dt. So this one cancels out, this one cancels out. So finally, we get is dG equals negative S dt plus dV dP. Okay. So this is going to help us with this. So we know that our differential amount of change in our Gibbs free energy equals this. So if we take the derivative of what we just found, that our Gibbs energy of the volume equals our Gibbs energy of the vapor, this can help us. So we have dGV equals dGL. Okay, so now let's bring in the equation that we just derived down here. So now we have is negative S volume times dt equals plus our V dP equals our negative SL dt plus RV. Oh, we're going to want to put this in our vapor as well. Vapor dp, and this is going to be our liquid dp. Okay, so now that we have this, we know that we can see that this over here, we have dp on this side, dp on this side, and we have dt on this side, and we have dt on this side. So we can combine the two together. Okay, so let's bring dp on this side, and then dt on this side. So we'll have, well, we get to bring dp. So we have our volume at the vapor is going to be minus the volume of our liquid. dp is going to equal, now we have our SV, so our entropy at our vapor minus our entropy in the liquid, dt. Okay, so now if we bring this over, we'll have dp over dt, and bring this over, we'll have v over, we'll have our vapor over that. So we'll have v of the differential amount of change of pressure divided by differential amount of temperature equals our entropy in the vapor minus our entropy in the liquid over our volume in the vapor minus our volume in the liquid. Okay, so now that we have this, we know that our differential amount of change of our entropy, our enthalpy equals T ds plus V dp, right? And we know that there is no heat added. Well, we know that it's going to be equilibrium. So we are going from a liquid to a vapor phase. So that means our pressure is not going to change at the moment. So this means that VdP is going to equal 0. So now that we have our differential amount of change, an entropy is going to be, an enthalpy is going to be over temperature equals our differential amount of change in entropy. So now we know this. So of our equation, we can see that it's entropy minus our vapor minus our entropy at our liquid. So that is the differential amount of change of our entropy. So we can plug this in for here, and we'll get our equation. So we have dp over dt equals enthalpy of the vapor minus the enthalpy of the liquid over T times our vapor in our volume of vapor minus the volume of the liquid. Okay, so this is the Clausius part of Clausius-Clapeyron. So we are saying the Clapeyron. Clapeyron means it's an ideal gas. So that means EV equals nRT. Right? We can say that this is just our volume. Our volume of the entire container is not going to change. So we can just have it as our volume. And also that this right here is going to be our heat transfer of a vapor. This is going to be our heat vaporization. And that is delta H vac. Delta H vac. So you can write delta H vac over temperature times just our volume of the container. So now that we know, now that we know our liquid, we can solve it. We can plug it in. to this, which is the ideal gas we can use for dinner. Okay, so then pressure is going to be on top, so pressure times our delta H VAP over, we'll have R and then T squared. Okay, so now at this moment, we have pressure and we have temperature. We can do a differential, we can integrate both sides and separate our values. So this is a differential equation. So let me erase. So we have dP, and then we'll move the pressure on this side. So it'll be 1 over pressure equals R H VAP and over R, and this is going to be our constant. And then we're going to have 1 over T squared over VT. And then let's integrate on both sides. So this is going to be based off of P1, P2, and also this is going to go from P1 to P2. So now we have is our natural log of P2 over P1 is going to equal, and since this is a -2, it's going to be negative, but if we flip it, it'll be positive. So we're going to do as positive first. Delta H VAP over R equals, and since I made it a positive, this means that T1 goes first, and then T2 comes last. And this is our Costas-Clapeyron equation right here. So, thank you.